All right, today I'll be talking to you a little bit about one of our projects focusing on how do we improve the durability of mass timber structures, namely specifically CLT. This project was born out of, wood decay is an issue for mass timber because mass timber is made out of wood, in case you didn't know. So fungi in our area, fungi are the primary agents of decay for wooden structures. And this goes for mass timber buildings as well. Just a couple of pictures here, student Ph.D. student in our department here, Kenneth, has been rotting these large pieces of CLT, and he can confirm to you that it rots pretty well, loses a lot of strength. And this will happen if all the appropriate agents are present in the case of decay. So when a tree is cut down, it actually already contains fungal propagules that will digest it if all the proper conditions are there. So for mass timber buildings and most stick frame buildings in general, the primary mode of protection is water exclusion. So fungi are not able to decay wood unless there's free water in the wood above roughly 28–30% moisture content. And that's the major component of this decay equation that gets taken away in order to protect these structures. So you need water, air, food, which is the wood itself, fungus, and appropriate temperatures. All of those components except for water are going to be there in a building environment because we also like a lot of the same things that the fungi like, except for being underwater, or also, well, we're not going to have our buildings underwater. So that's, yeah, that's one of the things we can exclude here. So again, building envelope, moisture exclusion, making sure the structural elements are dry is kind of really the main line of defense here for protecting these structures from decay. Moisture management fails, or moisture management does fail sometimes though, particularly these buildings are particularly vulnerable during construction. So this is before my time at OSU, but this is a picture taken, I believe, by my predecessor, showing PV Hall with quite a lot of water on some of the floors. So PV Hall will be fine. It's a very closely monitored structure, but as more and more of these buildings are built, moisture is going to become an issue. Decay is going to become an issue because moisture exclusion is never 100% throughout the life of a building. All right, so what's our second line of defense? So if you think back to that decay equation I showed, we have some other methods we can use to take away elements of that equation. One of those is the food aspect. So we can make wood unpalatable to fungi. Typically how that's done with dimension lumber is through pressure treatments, also surface treatments or dip treatments with biocidal chemicals. One of the more common ones is copper-based formulas. But in the case of appearance products, things that would be used in, say, mass timber construction, some of our less discoloring preservative formulas are more relevant, things like borates that are useful for above ground contact applications. There's a lot of challenges though incorporating these into mass timber panels. So mass timber panels are big and pressure cylinders are not as big. So that's a major factor. Largest cylinders you typically get are about 12 feet in diameter. And I think you all know that mass timber panels can be bigger than that. And those large cylinders are typically for some of the heavy duty preservatives anyway, like creosote. So you're not going to be creosote treating mass timber panels. So waterborne treatments that are used for these above ground contact applications, they're waterborne. So when you if you were to treat a panel with waterborne formula, you've subjected it to a wet dry cycle, and that can cause some issues with checking and deformation of the panels. I've got a picture of some of our experimental size stuff. These are really small 18 by 30 inch panels that were subjected to pressure treatment, but you can see after you've got these nice square mass timber panels ready to go up in the structure, you've subjected them to a wet dry cycle, and now they're out of shape when they get to the job site. So that's not ideal. And perhaps the one of the biggest issues with another option, instead of actually treating the panels post layup, is to use pressure treated lumber in the manufacture of the panels. Problem there is that you have to plane the stuff before it goes into the panels. So where's most of the preservative in a pressure treated piece of lumber? It's in that outer ½ inch or so. How much do you plane off when you put these into panels? So you're planing off quite a lot. And we've got some data that shows with this project that you lose about 66 to 89% of the chemical in that outer 0.4 inch zone. So a lot of problems with incorporating these in. I'd also just like to make a mention that inclusion of preservative treatments in mass timber construction is kind of like an extra layer of insurance. You've got the water excluding barrier. If that stays intact, you're fine. You're not going to foster the decay of or the growth of decay organisms. But if it doesn't, then you've got a problem. And so having an extra line of defense is a way to give yourself a little extra insurance. So right now we've got a small test looking at several different preservative and resin combinations. Another issue here using pressure treated lumber is interactions with the resin. So some of these don't seem to work well, but we've got a small scale test looking at melamine formaldehyde and polyurethane resins used to make some small panels that are in combination with one of 3 different types of pressure treated lumber. These have been, I had a student characterize these for their structural strength properties, did a little microscopy of the bond lines, and also we have these sitting out at a active Formosan termite site on Oahu in Hawaii. So I had the student working on this did some delamination testing and block shear tests as described in the PRG 320 standard. Essentially, we've got an all organic compound based preservative system, borates, and then a dip treatment of borates. So one borate treatment with with more or less chemical in there. And our borate treatments did not perform well in delamination tests. They seemed to have some trouble with melamine formaldehyde and polyurethane resins. The all organic treatment appeared to perform better. I had the student take a closer look at the bond lines to see what the mechanism of this was. And sure enough, what he found is that when he looked at the CLT under the microscope, he found a little bit more resin penetration in the all organic preservative treatment versus the borate treatment. So there appears to be an impact of the borate treatment and how far the resin's actually able to penetrate. And that could be due to a number of factors, but we'd like to pursue this area a little bit more. And of course, we've got the panels still sitting out on Oahu. So we're waiting for them to get eaten up by termites. And then the idea is to do some CT scanning and look at the termite galleries and how extensive the damage is. We're aiming to get those taken out this summer. So to be determined. Remember, I said most of the chemical got planed off there, so it'll be interesting to see how much protection is left in those panels. One more thing that we've worked on a little bit is looking a little bit closer at the mechanisms of resin and preservative interaction. So I've had the student working on this project has done some dynamic mechanical analysis of active resin curing in the presence of these different preservative systems, just to get a little more fundamental information on what's causing the negative interaction we see, particularly with the borates. All right, so with that, I'd like to thank the funders and Cody Wainscott, who's done all the work for this project, and I'll pass it on to the next speaker.